So Jim, you and I will be pressing those buttons to admit people.
Yep, I've got it covered, Sri.
Okay, because I'm doing the review, the introduction, so I don't want to keep doing that right now.
Yep. Okay, Sri, whenever you're ready.
Okay, welcome everyone to the astronomy colloquium. And before I do the introductions, I just want everyone to know we have two sabbatical visitors, Roger Blanford in Kip Thorne's office and Jim Cordes from Cornell, who just arrived this week in Nick Scoville's office. They're both eager to talk to people not via Zoom, but to meet and talk to you, just letting you know. Okay, now to the colloquium. Our speaker today is Tony Readhead, who is an emeritus professor of astronomy at Caltech, and of course known to many of us who've been here for some time, and maybe not to the newcomers. He's also an honorary fellow at the 4th Institute of Astrophysics in Crete, Greece. Tony had and continues to have an incredibly broad and deep career. In fact, I started preparing this introduction early in the morning and I just about finished it. It's about a few pages long, about 15, I think. Tony, you may want to reduce the length of your talk by say about 15 minutes by the time I finish this introduction. Tony grew up in South Africa and he arrived at the Cavendish Laboratory, Cambridge University, right after they discovered the first pulsar. His PhD advisor was Tony Hewish. The Cambridge group under Hewish's leadership had developed a large 20,000 square meter dipole array working at 81.5 megahertz, primarily to use the technique of interplanetary scintillation, which arises, as some of you know, in the solar wind, to in fact study fine structure of radio sources, cosmological radio sources. It's an inexpensive way to do arc-second studies without interferometry. Tony's landmark 1972 paper established that interstellar scattering and scintillation was widespread, even at the galactic poles. And it's a major feature of the decimetric sky now. Tony joined Caltech as research fellow and rose rapidly to become professor and then eventually the director of the Owens Valley Radio Observatory. He vigorously led the VLBI program at Caltech. Along with Peter Wilkinson, Tony invented the self-calibration algorithm, which formed the basis of VLBI imaging and high dynamic imaging in connected interferometers such as VLA. In a universe without cosmological constant, CMB fluctuations were expected on fine angular scales. So one day, Tony boldly leaped from VLBI to CMB. He was the principal investigator of the Cosmic Background Imager, CBI, at Chasnantor Observatory, Atacama, Chile, the first CMB experiment aimed at high angular resolution studies. In aid of CBI, Tony and his group partnered with industry and greatly improved the quality of microwave monolithic integrated circuits, i.e. mimic amplifiers. Essentially mimics of wideband plug-and-play RF amplifiers which can be operated without much fuss and muss. Mimics made it possible to pave the way to develop focal plane camera arrays such as COMAP that our own Kieran Clary is now leading at Owens Valley Radio Observatory. Over the last 20 years, Tony pursued the world's largest radio monitoring program using the 40-meter telescope at OVRO. This program worked with Fermi Glass mission and is aimed at elucidating the nature of blazars. The exciting result in 2014 of polarized signal from BICEP and Keck array soon became accepted as not due to some cosmological process, but as arising to dust particles in our own galaxy. Tony immediately organized a major program aimed at mapping the polarization of bright stars so that this foreground can be modeled and then the delicate CMB signal can then be inferred from that. This program has finally reached fruition with data collection around the corner. Well, you can see that, but I think since Tony has to give a talk, let me stop the introduction and end with a few personal anecdotes. I met Tony, I think in 1979 when, because Caltech was a major center, in fact, was the center for VLBI. It had a big VLBI correlator, and I was spent at that point in my second year pursuing a potential PhD in dual polarization VLBI. Thankfully, I developed a second sense and moved away from AGN and dual polarization VLBI, which turned out to be a wise move because it only became possible 20 years later with the VLBA. So I switched to doing interferometry still, and Tony was very helpful as director of OVRO in actually giving me, initially a loan, but then giving me an L-band feed that was no longer in use, which allowed me to build a radio-linked interferometer in Puerto Rico. I would say the person who lured me to Caltech was Tony. Tony has, one thing I like about Tony is a tremendous sense of humor, even at his expense. I would make many jokes and continue to make many jokes about vermin of the sky, AGN, the usual sorts of things I do. And that we used to have skits at Owens Valley, and Tony would always be caricatured in some sort of a thing where I would, of course, make fun of Tony, and we still remained friends. I learned another thing I would like to say is Tony, as you can see, has organized very large projects on different continents. And you require a lot of money for that, not just ideas. He is the undoubted master of the universe in wheeling and dealing, to whom I remain eternally grateful. At his feet, I learned the rather fine art of W&D. Tony still continues to rush around as he used to. Jim and I called him up and said, Tony, we wanted to be on at 3:50. We want to check all this stuff. I said, it's not 4 o'clock because probably Tony's busy finishing a paper. In fact, at some point, it was so rushing around that it started introducing Tony to people as, oh, his Professor Readhead, he studies neutrinos. Of course, the joke was neutrinos have very little cross sections. They're there fleetingly. Well, I'll end this talk by saying Tony, in fact, has now genuinely gone from, is now a professor who's genuinely looking for astronomical neutrinos. Tony, the floor is yours.
Thank you very much, Sri. Thank you for the very kind introduction. Much appreciated. I also want to thank Nancy Kasdawal, who approached me a couple of years ago and asked if I would give an astronomy colloquium, and then COVID got in the way. And so thank you to Nancy and Jim and the colloquium committee. Thank you very much the kind invitation and for giving me this opportunity. It's always very exciting to give a Caltech astronomy colloquium, so I'm delighted to be able to do this, and just sorry we can't all meet in person. Okay, so what Mansi and Jim and the colloquium committee asked me to talk about today was the work we've been doing on the 40-meter telescope, as Shri has indicated. Since 2008, we've been monitoring about 1,800 active galactic nuclei on a cadence of 3 to 4 days. And it's a legacy program because this is literally the only radio telescope in the world that can monitor thousands of blazars on a cadence even approaching this. And when we first said we were going to try to do this, there were quite a lot of skeptics in the community. I'm happy to say not at Caltech, but in the community who thought this would not be possible, that you would monitor with high precision and accuracy thousands of radio telescopes on a 3 to 4 day cadence. Because we're now looking for neutrinos, and we'd like to basically have a target source in each of the IceCube footprints when it finds a high energy neutrino event, we started last year monitoring a larger sample, 5,558, very carefully selected blazars on an 11-day cadence. We don't need the shorter day cadence very much at say 15 gigahertz, which is our operating frequency on the 40-meter telescope. It's also, nearly all of those are also being monitored on the ZTF in RNG bands on a 2-day cadence. And the Cambridge arc-minute microkelvin imager, AMI, is monitoring any of our objects that are within 2 degrees of an IceCube event on a cadence that's no longer than a day. They can monitor for as long as we like and as quickly as we like. So this is a very powerful program and nobody else can match it. And we think it's very important because the identification of the electromagnetic counterparts of neutrinos is very important in our view. So the areas impacted by this are in extragalactic astronomy. It's amazing. I think a simple monitoring program can impact all these different areas, but it's literally the case that these areas have all been impacted, and the work I'll be describing today will address quite a few of these areas. I won't go through them in detail, but very happy to answer questions about them. So the Owens Valley Radio Observatory is a very beautiful place and very special place, one of the most beautiful spots on the globe. And this is approaching it from the east through the White Mountains, the Inyo Mountains on the east of the valley, which rise to about 14,000 feet. And we're looking across the valley to the Sierra Nevada over in the west, which also rises to 14,000 feet. And the valley floor is at 4,000 feet. So it's a beautiful place for a radio observatory with a lot of shielding, and was very well chosen by John Bolton back in about 1956. From the valley floor, if you look east out of the mountains that we just moved out of, this is looking back at the White Mountains from the valley floor with the 40-meter telescope in the foreground. And then looking west here at the Sierra Nevada, you can see why I say it's one of the most beautiful spots on the planet, because there's 10,000 foot of relief that goes for about 150 miles. And it's pretty spectacular. It's also a very nice place to be because the people at the Owens Valley Observatory and in that area are fantastic people to work with. So I want to tell you a little bit about the observatory, what's been going on recently. So this is obviously an aerial view, and you can see on the lower right there, you can see the 40-meter telescope. That's the 40-meter telescope, and then to the left of it, the two 27-meter telescopes, and right over about 3/4 of a mile over towards the left there, you can see the buildings that we live in. And in 2004, when the millimeter interferometer moved to the Karma site, we were concerned that there were no Caltech science programs on the valley floor. So we decided to promote a renaissance of activity on the valley floor with Anila's blessing. Anila Sargent was the Owens Valley director at the time, and she was very supportive of us doing this. And the display we've just gone through shows what we built up between taking the 40-meter telescope out of mothballs in 2005 and the present. And so Anila was, as I've said, she was very supportive. And of course, Anila was also the inaugural director of Karma. And before going on, I just want to say a few words about Karma because, of course, Karma grew, first of all, out of the millimeter interferometer at Owens Valley, which Nick was the chief builder of. Obviously, Bob Layton built the dishes. Dave Woody built a lot of the antennas with Bob Layton. Tom Phillips played a huge role. But Nick really, from 1986 until the mid-90s, he was the one that pushed this forward and made it into a world-class instrument and did a fantastic amount of science. And then Anila took on the mantle, the flaming brand, I could say, in her hand, and she and Anila created Karma, which was an incredible creation because it brought together the Celtic Owens Valley Military Array and the Berkeley, Illinois, Maryland collaboration, which were the two strongest groups in the world doing millimeter interferometry. And it was because of those two groups that ALMA became a reality. So I would say not only because of the science they produced, which was fantastic, opening up many new areas, but also because it gave the whole world this absolutely incredible instrument, ALMA, which, you know, is being so widely used on so many things nowadays. That's a fantastic legacy from the Owens Valley. But there was a danger when ALMA moved, when the millimeter interferometer moved up to the high side and we had nothing going on the valley floor, that if the Karma funding was ever cut, we would be stuck. So 2005 or 2004, 2005, as I say, with Anila's blessing, we started working towards this. And the first thing we did was to bring the 40-meter telescope out of mothballs. And I do want to say particular thanks to Fiona Harrison, the Keck Institute for Space Studies, Tom Prince and Michelle Judd, and of course at Owens Valley, Dave Woody and James Lamb, here on campus, Kieran Cleary, who are the architects of COMAP. COMAP is very important because COMAP is what enabled us to retain a critical mass of star from 2015 to 2018. And that's what enabled Greg and Vikram to successfully propose LWA 352 and DSA 110. So that's why I've sort of highlighted COMAP here, because had we not had COMAP, I think there was a serious danger that we would not have been able to continue, or at least we would have been a very, very small operation. But thankfully, the division kept supporting us. And we also got $1 million from when Karma closed down to help with COMAP. That was incredible. So I'm just going to be talking about my projects today. And so these are the projects that I'm working on at the observatory. And you can see the key up there of the staff, undergraduates, graduate students, postdocs, and faculty. I'm only going to be talking about the 40-meter telescope project, this one over here, and a little bit about this project, which Sri mentioned. And I won't be talking about the other projects today, but I just wanted you to see them, to know what's going on. They're all very productive. And our key aims on all these projects are, first of all, the work should be fundamental to the field. Second, the project must attract students and postdocs. And then we should be prompt, the papers should be prompt and well written. And I think we're doing well on those fronts. So here's a picture of COMAP. I just wanted to show you that. I will not be talking about this. As Kieran Cleary is the one who's the PI on this. And they've just put out a beautiful set of papers with their first results on this project, 8 or 9 papers that have just come out. I've got this lovely picture that Greg gave me of the LWA, absolutely gorgeous picture showing the LWA. And then this is a picture showing just part of DSA 110, which is Vikram and Greg's brainchild. And as you probably know, on the basis of the success of these instruments, they're now pushing for a DSA 2000 array, which would be absolutely phenomenal. It would be an extraordinary facility. We don't have time to talk about it now, but there was a 2-day workshop last week, and it was truly amazing what they're going to be able to do with that instrument. So onto the 40-meter telescope programs. So it was invented originally to do multi-wavelength studies, mainly with Fermi LAT, but these other programs also work with us a lot, ultra-high energy programs, HESS, MAGIC, Veritas, and of course CTA will as well. And then multi-messenger studies, relativistic jets, I'll be talking about that today with IceCube, and Terry's and Baikel are also using our data. Gravitational lens studies, relativistic jets, I'll be talking about symmetric achromatic variability. And then quasiperiod oscillator studies, in particular, supermassive black hole binaries. I'll be telling you about Parkes 2131-021, which we're very excited about. And then over on this side, the polarization studies, optical polarization studies that Sri mentioned. So I won't be spending any time at all on these this old legacy program. It's producing a paper a month. It has been doing so in referee journals since 2008. And the key result is we found that the radio emission lags at 15 gigahertz, lags the gamma rays typically by about a year, and is located further from the supermassive black hole by tens of parsecs, and that the lag decreases to 0 by about 100 gigahertz. That's because it becomes optically thin at that point. So I would say that's a success, that continues, and the community continues to work with us very much on that, or we work with them. But the things I want to highlight are the Multimessenger study, the supermassive black hole binaries, the gravitational lens studies, and the polarization studies. So one of the benefits of being an academic is that you have the tremendous pleasure and privilege of working with extremely clever, enthusiastic young people who seem to me to have infinite energy. And they absolutely keep me on my toes, which is a wonderful thing to happen. So here I'm picked out the people I've been working with. All of them have are either first or second authors on one of the papers I'll be describing today, except for Sid Maharani. He's the first author. Oh, I should say I've been working very closely with all of them except Sid. I put Sid on there because he's the first author on the key pacify optical polarimetry paper. He building that instrument and designing that instrument was Sid's thesis project. So I haven't worked closely with him, but all of the others I've worked very closely with, and they have all sweated bullets on the papers I'll be telling you about today. And it's just been incredibly exciting to be able to be working with them. So these are the 4 projects I'll be describing. I'll go through in that order: Multimessenger, supermassive black hole binary, millilensing, and then 4 polarization studies. So to begin with Multimessenger astrophysics, IceCube at the South Pole. I begin each of these 4 chapters in my talk with a different cartoon from Sidney Harris. And in case anybody's worrying about copyright, I've been in touch with them, and they've given us permission for a small honorarium to use these and have them on the Caltech archive movie, and to make slight adjustments to them where necessary. This cartoon was not originally standing next to IceCube, but I think it shows exactly what we're hoping to do with IceCube. Just checking. We want to find out where IceCube's astrophysical neutrinos are coming from. We've only just started this program. We've done a bit of work in this area, which I'll describe very briefly, but I'll mostly be telling you about what we're going to do. So please don't be disappointed if I don't end up with some key results with IceCube. We haven't done it yet, but I'll show you what we're planning to do, hoping to do. So as there was the first talk this year, the winter term, was Ignacio Tabardo's beautiful talk on the 5th of January. Very fortunate for me because I don't have to repeat. I hope many of you or most of you were at that talk, a very nice talk. And I don't have to repeat what Ignacio said, but it was a very nice introduction. But just let me remind you that this is a lab at the South Pole, literally, and the bedrock is nearly 3 kilometers below the ice. And what they've done is to drill these 86, boreholes into the ice using, high pressure, high temperature water. And they've inserted 86 strings of optical sensors with 60 optical sensors on each string. And the optical sensors start about 1.5 kilometers below the surface of the ice. At that depth, you get down to where there are no bubbles and that sort of thing. And the ice is beautifully transparent. And so it's really where you want to be. And so they've built this amazing 1 cubic kilometer detector. It's a truly extraordinary accomplishment. So what about, obviously we want to know about the sources, and all of these objects that I've, classes of objects here that I've listed have been suggested as the possible sources of the high energy neutrinos that IceCube is seeing. And probably the most popular of all of these is active galaxies. And the sites for the neutrinos have been suggested going all the way from the accretion disk all the way out along the jet at multiple sites. So it's very complex. Then you've got starbursts, supernovae, gamma ray bursts, etc., tidal disruption events, white dwarf, etc. If none of those turn out to be the sources of the high energy astrophysics neutrinos, then it may be that it's dark matter, or people think it could be physics beyond the standard model. But clearly, it's very, very important to try and identify the electromagnetic counterparts of IceCube's high energy neutrinos. So we'll be doing it with active galaxies, but the problem is there's over 1,000 active galaxies in each IceCube high-energy neutrino position. So positional coincidence is not enough for confirmation of an association. You need more than that. I'll be describing what we're doing about that. So we've picked out these just 5,500 blazars, and we're observing them on this 11-day cadence with the 40-meter, 2-day cadence with ZTF, and 1-day or better cadence. Sorry, I've got to get rid of that. So I hope this isn't gonna, oh dear. I think I've just lost you. Have I lost you, or can you still see my screen? This happened to me before when I was preparing, that this message kept on coming up. Anyway, let's hope it doesn't happen again. Okay, so we're picking, these are blazars, these objects, and so they're objects with a relativistic jet pointing towards us. Now, if you look at the jet in the rest frame, and I show this in this little picture up on the left here, think of all the radiation or all the particles that are being emitted into the 2 pi steradians on the right-hand side. When that object is moving relativistically towards you, all of those particles or photons, etc., appear to come from a much smaller cone angle, angle of 1 over gamma, where gamma is the Lorentz factor. So typically, if the relativistic jets are emitting neutrinos, then the neutrino flux is boosted by gamma squared is about 100, and the energy boosted by gamma about 10 relative to the rest frame. So clearly, looking at blazars is a very good way to try to look for sources of neutrinos, because there's lots of processes in blazar jets that can produce neutrinos. And then we benefit from this beaming effect. So to talk a bit about relativistic jets, here's a very nice multi-wavelength image of Cygnus A. And the great thing about the radio is the red, the optical is the white, and the blue is X-rays. The wonderful thing about radio is that radio observations are a very good proxy for the energy output of the AGN central engine. And so it's a good way of figuring out how much energy is being coming out. Now, Cygnus A is almost, the jet's almost sideways on, almost in the plane of the sky. So there's no relativistic boosting. But if you look at M87, it's about 17 degrees to the line of sight, the jet angle. And so there is boosting, and that's what's responsible for the asymmetry and why you see the jet coming out mainly on the one side in M87. Now, if you take an object like that and you turn it so you're looking right down the jet, of course, you end up with a quasar like 3C273, where you see the optical, this is a Hubble Space Telescope image of 3C273, where you can see the optical center of activity boosted hugely by relativistic beaming and the jet boosted by relativistic beaming. So how are these relativistic jets launched? This is one of the major questions we want to answer and that we address with this program of the 40-meter telescope. And the two sort of, I won't go into this in detail, but the two processes that we're focusing on mainly are the Blanford-Znayak process, where the energy is extracted by the spin, the energy in the spin of the black hole. And then the other one is the Blanford-Payne process, where because of the because you've got the magnetic field which is tied to the spinning plasma, you get particles slung out along the magnetic field lines like wires, like beads along a wire. So we're looking for at this Blanford-Znayak and Blanford-Payne. There are other processes, but that just helps us to think of what we're looking for here. Another question is, what is the composition of these relativistic jets? Are they leptonic or are they hadronic? If they're hadronic, then they're almost certainly also the origin of the ultra-high energy cosmic rays, which has been a mystery for 60 years, and I'm sure you know. So thinking about the multi-messenger universe, first of all, think about astrophysical gravitational waves. The beautiful thing about gravitational wave astrophysics is that we know what we're looking at and we know what we're looking for. Each type of detectable gravitational wave emitter has a very distinctive signature. Here's this absolutely beautiful result, the original result from LIGO. It's very different in astrophysical high energy neutrinos. So here are three of the possibilities: active galaxies on the top, gamma ray burster, and then tidal disruption events. These are very messy events, and they don't give a clear signature. It's a very difficult field. We don't know what we're looking at, and we don't know what we're looking for. There are no known clear-cut signatures. And one of the things we want to do in this program is to see if we can find some clear-cut signatures. So this makes this last astrophysical window, which IceCube is so brilliantly opening up for us, a much more challenging search for EM counterparts. But the variety of objects is likely much larger. Now, one thing I want to make clear is that at present, we're in the stage where we only see one high-energy neutrino from each source. Okay? It's very difficult. I just want to show you again some of what Ignacio Tabardo showed us on the 5th of January, but I won't spend a lot of time talking about it because he gave such a beautiful exposition of the interactions on the left that are producing the neutrinos that we're looking at. And then one thing I should mention is these two types of event. There's the cascades or showers, which we won't be talking about on the right there, which is when the interaction with the astrophysical neutrino occurs inside the volume of IceCube. And then there are these tracks, which is where the interaction with the astrophysical neutrino occurs outside the volume of IceCube. And there's a muon that goes flying through the IceCube detector, and you can measure its track through the detector. And it's just a beautiful experiment. It's pretty amazing. Ignacio spent quite a bit of time explaining on the 5th the evidence and giving us the evidence for the demonstration that a significant number of the high energy neutrinos from observed with IceCube are of astrophysical origin. I don't have time to go through that, but if I picked out the 3 slides from Ignacio's talk that he sent me kindly after his talk. And if any of you are interested or didn't see that talk, follow up on Ignacio's talk where he gives a detailed explanation. So here's a beautiful artist's rendition of 2 events, a shower on the right, which we're not going to be thinking about, and a track on the left. And this just shows you one of their optical sensors. And the size of the bubbles on these tracks shows you the amount of energy, or the number of photons, I should say. The smallest ones are just 1 photon. So the most famous result from IceCube that's associated with an AGN is Texas 0506-056, and this is the track through showing how that neutrino, how those muon from that neutrino passed through the detector as it went through IceCube. There's a side view and a top view shown there, and the actual result showing you the footprint is here, and you see from that red contour that the IceCube 90% area is about a square degree. Now, it's for this reason that we're going to be looking at objects, everything that's within about 2 degrees. We've, in our sample of each IceCube event, because we just want to be careful that we don't miss something interesting. And what IceCube concluded was, shown on the bottom there, further observations will be needed to unambiguously establish a correlation between hydrogen neutrinos and blazars. Okay, so that's a 3 sigma event. Now, I want to briefly mention the observational state of the art. For trying to identify active galaxies, just concentrating on active galaxies with high energy neutrinos. And so here what I've done is I've laid out on the top here, there are the 4 that have been discussed in the literature, coincidences of IceCube events with active galaxies. And the 2 at the bottom are ones which were picked out by, this one's Baikal, and the other one's, oops, sorry, I've got to go back, sorry. Sorry about that. Okay. Bottom left shows a preliminary result from Antares under the sea, and bottom right shows from Baikal. All of these these apparent coincidences, except for the NGC 1068 one, when looked at with the, when compared with the OVRO light curves, show that there's some activity going on at OVRO. And so there's possibility that there's actually a correlation. It's by no means proven, I would say. You can also notice from the vertical purple lines, that's a time of arrival of the IceCube neutrino. And on the top 3 curves, which show the Fermi gamma ray emission, as well as the arrival time of the IceCube event, your neutrino, you see that gamma rays seem to be being suppressed when the neutrino rise. And of course, we shouldn't be too surprised if that's the case, because if you've got a lot of events going on in this plasma, in this relativistic jet, and you're producing a lot of photons and high energy particles, those photons are going to scatter the high energy gamma rays by pair production, and so it becomes optically thick. So it may be that just when you're seeing the neutrinos coming out, you're going to have gamma ray suppression. So that's one of the signatures that we'll be looking for. The time-integrated neutrino source searches from this is the most authoritative result, is that it looks like there's a 3.3 sigma significance from IceCube's own analysis. The problem with single electromagnetic event counterpart approach is that it's all a posteriori. And given that there are over 1,000 AGN that could be associated with any particular high energy neutrino event, you're always going to be able to find an AGN doing something strange that could be an association. So you're going to want to look at samples. And so there are two big samples that have been looked at, radio samples, one by Plavin et al. And one by our own group, Havata et al. And basically these lead to sort of 2.9 sigma or 2 sigma significant coincidences. So it's clear that we do not know, and that we really need to follow up on this. A nice thing that IceCube's begun doing recently is they've begun giving us these real-time neutrino alerts, the gold and bronze alerts, where the gold are at least 50% likely being astrophysical, and the bronze are between 30 and 50% likely to be astrophysical. We want to be looking from the northern hemisphere, because if you do that, then you shield the Earth shields out the atmospheric muons and so on that are going through IceCube. So you really want to be careful and use a telescope in the northern hemisphere if you want to be doing association with IceCube. So you want to shield against the downgoing electrons that IceCube is seeing and get the upgoing ones that have come through the Earth. Okay, so I'm going to, because of this a posteriori business, Roger Blanford, who we've been working closely with ever since we started this program in 2008, or a couple of years before that actually, he was very insistent, and I'm glad he was, that we write down our hypotheses before we actually begin the observations, which we have done here. And I'm just going to quickly go through this, not to try to, I don't want to bother you about all the detail here, but I just want to show you what the next few things on the slide and the next slide, just to show that we've done our homework correctly. So basically, IceCube has given us their projected numbers of events over the next, from 2021 to 2025. And you can see that they're projecting that there will be 42 gold events and 18 bronze alerts, and 42 astrophysical gold events and 18 astrophysical bronze events. And you can see the non-astrophysical numbers there as well. You need to choose your sample carefully, and I'm not going to go through this in detail, but this is just to show you, this was how we arrived at our sample of 5,500 objects that we're monitoring. And we've done it very carefully, and 3 of these are complete samples, the one with asterisks, so we can do very good statistics on them. And then these are the tests of our hypotheses. How are we going to test them? I'm not going to go through those. A very important part of the test is you want to be able to simulate accurately what's going on in these sources. And so for this reason, what we do is we have a simulation program that was actually, it's built on this beautiful paper by Amanolopoulos et al. But basically, we generate artificial light curves where the power spectral density and the probability density function are consistent with the light curve. So for every object that we look at, we can generate thousands of these light curves that have the same statistics as the light curve we're looking at. This just shows you an example. It turns out that only 6% of our light curves are well fitted by a Gaussian PDF. And if you don't use this Amanolopoulos approach, then you end up producing Gaussian PDFs if you're not careful. This shows you a typical one of our objects here, which has its 2 Gaussians. So we use that approach to generate many thousands of light curves. And one of these is a real light curve, and the other 3 are simulated or are fake simulations. So I challenge you to tell me which is which. I think it's not possible to pick the right ones out. So IceCube Gen 2 is the next step, where they want 10 cubic kilometers They're aiming towards this. And this is the end of my first part of my talk. I just want to end up by saying that the OVRO telescope provides unique opportunities to search for the most likely and most promising of neutrino EM counterpart candidates, jetted AGN. Greg has generously committed 90% of the observing time on the 40-meter telescope to this program for 3 to 5 years, contingent on funding. And I would say due diligence requires that we do our best, the best possible job to search for these electromagnetic counterparts. Okay, on to the next part, part 2, quasi-periodic oscillations and supermassive black hole binaries. I feel just like this cartoon of Galileo, because some of the things that we found when we started looking at the source just shouldn't have happened the way they did. Okay. We're studying the quasi-periodic oscillations in our 1800 blazars. This program is being led by Yannis Leodakis. And then in January of 2020, we got a paper from this group in China who told us that monthly notices have told them they better check with us because they weren't sure they'd interpreted right. They said it was a supermassive binary black hole, and we thought it's another quasi-periodic oscillator. And for about a week, we were going to combine with them and write a paper together. But then we realized that the amount of analysis we wanted to carry out was much more than they wanted, because they wanted to get this paper out quickly. So we sort of, fine, go ahead. We can't do the analysis on your timescale. Go ahead and publish the paper, which they did. So meanwhile, we started working on this, this data. And I took that, this is the OVRO light curve that you see in the blue dots on the right, and fitted a least square sine curve to it and extrapolated back, because we thought we'll look back and see if there's any record of this going backwards. And so our first prediction was there should have been a peak before we started observing. And Matt Lister had some nice VLBI results, and he immediately emailed back and said, there is a peak, this is great, prediction verified. And then we got hold of some Michigan results, and we found that there was another peak that coincided in phase all the way back in 1982. So, okay, I know that this is, you know, there are stuff in the middle that's not coinciding, but it looked like there could be 2 predictions there. And if prediction true was true, I said, well, I wish we had been observing this before 1980, because it looks like there was probably a big sinusoidal fluctuation before 1980. But unfortunately, it wasn't being observed. But so our prediction 3 was there should have been a peak there, and it should have had a large flux, a large amplitude variation. So I thought that was it. But fortunately, Sandra O'Neill decided to work on this for a surf last summer. And I thought I'd better do a literature search to make sure we hadn't missed anything. And blow me down, I came across a paper by Chris O'Day where they observed the source from 1976 to 1984. And if you look at the 15.5 gigahertz, you'll see there's something that looks, wow, pretty good there. So I added that on, and then we fitted a least square sine wave fit to that. And the periods tie up to within 2%, and the phase ties up to within 10% of a period. And there's a 20-year gap in the sinusoidal fluctuations in the middle. So we all thought this was very significant, and we started working hard on it. We divided the data up into 3 epochs based on various tests that we did that I won't go into. And basically, we think what we've discovered is a new and completely unanticipated phenomenology in supermassive black hole binaries. First of all, sinusoidal flux density variations, which nobody had predicted, but we can explain. 10% changes in period, which we can also explain, and large gaps in the sinusoidal variation. So we think this is very exciting. I'm not going to have time to go through this in detail, but basically, if you do tests using our simulation software, and you apply a generalized Lohm-Scargill test of the power to the sinusoid in the OVRO measurements, you find that that's significant at the 3.35 sigma level. So we think that's not just a random fluctuation due to red noise in the variability spectrum. That's real, that 3.35. That's test 1.3, you can see there. If you then take that period and you look within a small window given by the uncertainties in our periods in epoch 1 over on the left-hand side there, you find that you do find a peak with that period, and the significance of that is at the 2.06 sigma level. And these are two completely different data sets. So you're allowed to, the probabilities are uncorrelated. So you can multiply those probabilities and you end up with a 4.32 sigma possibility of randomly getting the same period in the first epoch and in the last epoch there. And if you then add in the 20% phase correlation, you get up to a 4.6 sigma significance. So we have no doubt at all that this is a real physical thing that we're looking at. I asked Roger, well, why is it producing this beautiful sinusoid? And he went away and thought about it. And the answer is amazingly simple, and it's very beautiful. As Roger pointed out, if you've got a jet where the material is already moving towards you with a high Doppler factor, in this case, it's a gamma of 15 or so, certainly above 10. So it's moving towards you at 99.9% the speed of light. And then you add a small amount of motion to the origin of that jet, let's say through the orbital motion in a supermassive black hole binary, blow me down, it produces a sinusoidal fluctuation. This is the working you can see on the right there. And it has about the right amplitude. What this means is any supermassive binary black hole that's producing a relativistic jet in a blazar is going to be producing sinusoidal fluctuations like this. So we think that's very exciting. Vikram did these sums for us, and also Michele Vallisneri at JPL. And it's interesting because it turns out that you can get a chirp mass both from what we measure in the radio, and you can get a chirp mass from nanograv, and they're about on the order of 3 times 10 to the 9 solar mass is the upper limit because it hasn't been detected. So anyway, that's pretty exciting, I think. So the conclusion to part 2 is I'm willing to bet a good case of wine that Parkes 2131-1021 is a supermassive black hole binary. A case of good wine, I should say. Okay, so any takers? So please stay tuned on that. Okay, I want to switch now to gravitational millilensing studies, and I'm going to go through this very quickly because I just want to make a couple of points. First of all, we're following up on this early work done with Peter Wilkinson that we published back in 2001, where we looked at 300 compact radio sources, for example, of multiple imaging with VLBI, and found none. And that enabled us to put an upper limit of 1% of the closure density on objects, on condensations with mass range of 10 to the 6 to 10 to the 8 solar masses, so millilenses we would call them. And we're now doing a search with 20 times as many sources, and Carolina Casadio is leading this search. And if we don't find any, haven't found any yet, then we'll be able to improve that limit by a factor of 20. I now want to talk about symmetric achromatic variability in Parkes 1413 plus 135. And I'm going to make a statement that this is the most peculiar blazar known, in the hope that somebody can prove me wrong, because if they do prove me wrong, they'll have found a very interesting object. I put this slide in here with all these details as a buffer, thinking that by the time I got here, I wouldn't have time to go through the details. But if I had time, then I would go through them. I don't have the time to go through these details, but you can see there are 16 different effects there that tell us this is a very peculiar source. One of them is that the optical axis of this edge-on spiral galaxy is normal, almost exactly normal to the radio axis. And that would tend to imply that the spiral galaxy is associated, the radio source is associated with the spiral galaxy. But we actually think the radio source is way behind the spiral galaxy. And you can read the reasons for that in the papers that, these papers that we published. Now, we've just had our latest paper accepted. The person who did all the work here, all the heavy lifting, was Lawrence Pearson at Stanford. He's a graduate student at Stanford. And on the top left there, you can see why these objects intrigued us, because the black curve shows our first observation of the symmetric achromatic variability, and the red curve shows that same black curve, but just reflected through the center of symmetry. You can see it's amazingly symmetric. The curve below that shows you different frequency observations, showing that it's achromatic. And then number C is an extreme scattering event that we observed in this program. And Harish Vedantam did a very, he did the early work on this. I should have mentioned that in the first 2017 paper, and he did a beautiful job on that. And he also did this very detailed study where you can show that this is definitely not due to extreme scattering events. Vikram took a Keck spectrum and showed that it's not a BL-lac as people had thought, but actually it's a Cepheid-2 galaxy. And you can show that we are outside the cone of emission in this object. So if you're inside the cone of emission, you could see tracks of components moving away from the core at all angles, as you see in C there. But if you're outside the cone of emission, then you're only going to see tracks confined to a rather narrow range of position angles. It was said to be a compact symmetric object, but we now know it's not. This is the curve that we're looking at. It's much more like a blazar, these two up here, than, whoops, than the other CSOs. And so we're now redefining CSOs, and we're doing a big study on that at the moment as a result of this paper. The top two curves show Harish Vedantam's original plots of the original two SAV events that we saw. And the bottom curve shows Lawrence Pearson's tracks through the caustics, which are producing the curves that you see at the bottom right there. Okay, these are showing Lawrence's fits. I don't have time to really go into that now. And I'm also going to only make one point here, which is if it turns out that this object is actually in the spiral galaxy, and if it's gravitationally lensed, as we think it is, then the question of what is the lensing body is very interesting. And of course, the fact that it could be sub-halo dark matter lens is very interesting. Yanis Leodakis did an interesting study because we were challenged to make a prediction. And it turns out that there is a bit of a periodicity here. And I can explain this in more detail, but I won't do, if anybody asks a question, I'm happy to do that. But the conclusion to part 3 of my talk is, I think there's a very good chance that the SAV in Parks 14, 13 plus 135 is due to Milli lensing. And I'm willing to bet not a case of good wine, but a bottle of good wine on this. So if there are any takers for that, I'm also willing to bet a good bottle of wine that the above periodicity will not hold up. I'm pretty sure it won't hold up, but on the other hand, it would be foolish to ignore it. Okay, the final part of my talk, I want to talk very briefly about the work that we're doing on the optical polarimetry, because I think it's very exciting. This is actually a cartoon by Sidney Harris from about the early 80s, and I've had the temerity to completely change all the captions here with Sidney Harris's blessing. And this is the inflation story, and I'll give you a minute to just read that so you can enjoy it. It's pretty amazing that we believe this inflation stuff, especially I like the fact that we can just ignore discrepancies of 10 to the 120. I think that's probably got to be one of the biggest discrepancies that's been ignored in science. I like that very much. So this project that I'm showing here, this paper was led by Gina Parapoulou, Hubble Fellow here at Caltech, and Clive Dickinson, who was visiting us, came here at the beginning of COVID and was here for 1.5 years sort of thing, which was great. On the left shows the synchrotron Planck map of angles. And in the middle, Gina and her collaborators, mostly Gina's effort, has collected over 20,000 optical stellar polarization measurements gleaned from the literature. And you can see the incredibly good agreement. It's clear that the star, what we're seeing from star polarization, stellar polarization, and synchrotron is the same thing. Very interesting. So what we're planning to do with this wonderful instrument that's been invented by Rama Prakash at IUCAA is we're going to build 2 of these beautiful instruments. They use the biggest Wollaston prisms ever made, as far as I know. And the beauty of these instruments is that they get the polarization in a single exposure. So you don't have to do anything. You don't have to have 2 exposures, between which the atmosphere could change by 1% or so, which would wreck the experiment. You wouldn't be able to do it. And what we will do with these two wallops, as we call them, one in South Africa and one in Crete, one on the 1 meter telescope South Africa and 1.3 meter telescope in Crete, is we are going to survey the patches, parts of the sky seen in dark gray there. Now, everything that's gray there are no stars per 1 square degree pixel. And you can see from the little diagram on the left that for the magnitude that we're going for, there are 200 stars per square degree at the galactic pole, and there are about 1,000 stars per square degree at 30 degrees galactic latitude. And we'll be surveying that whole dark gray area there, and we expect to find at least 4 million stars. So we'll be going from 20,000 up to 4 million. It's going to completely change the picture. And Rafael Skalidis, working with Kostas Tassis, they've worked out a theory which is an improvement on the older theories, where you can derive the magnitude of the magnetic field from the optical polarization measurements. And of course, we're going to combine all of this with Gaia, so we get a 3-dimensional picture of the galactic magnetic field. So we're very excited about this. And I just want to quickly show you the instruments. And then in summary, I'd like to say that the value of legacy studies should not be underestimated, especially in astronomy. We're looking at all these very interesting things simply by making flux density measurements with the 40-meter telescope. All of my co-authors and I owe a huge debt of gratitude to Fiona, to PMA, and to the OVRO director, Greg, and the OVRO staff, and especially to Dave Woody and James Lamb. I personally owe a huge debt of gratitude to Sri Kulkarni, Sturl Finney, Greg Hallinan, Vikram Ravi, and Kieran Cleary for their fantastic support, and especially during 2015, the dark days when funding had just gone and we were worried that we may have to close down most of what was going on at OVRO. Their hard work in 2 retreats, one at OVRO and one in Palm Springs, where we devised the OVRO strategic plan, which I'm happy to say has been fantastically successful, thanks to the genius of Greg Hallinan and Vikram Ravi. I also want to thank Roger Blanford and Neil Garrell, sadly no longer with us, but they enabled me to bring the 40-meter telescope out of mothballs. And I want to thank my colleagues shown below for their invaluable support. It's been absolutely critical to being able to do this program at OVRO. Thank you very much.
Okay, we will take some questions. I'd like, please raise your hands. There's bottom right of your Zoom window. There's a reaction button and you raise the hands, and after your question is answered, lower it. Otherwise, I'll think you have another question. So let's go, Mansi.
Thank you, Tony, for the fantastic talk. The question I had for you was in the second chapter. So this supermassive black hole binary, I missed how you explained the 20-year gap.
Oh, thank you. It's a lovely question. Yes, it's a wonderful, it's a great question, and it's something that the person who reviewed the paper was very exercised about, but he was happy with our answer. But I'm glad he was exercised about it because we emphasize it in the paper now. I think actually, Mansi, it's quite easy to do this with blazars, because we think that a lot of the variability that we see in blazars is influenced by the fueling. And so what we think we have going on here is you've got a blazar, which is chucking out material along the relativistic jet. Now, some of that material gets quite a long way out and goes on radiating for quite a time, and it is still changing and varying. So you're getting variability from out there. We think what's going on here is we're seeing much closer into the jet. I didn't have time to go through it, but that variability that we're seeing, those sinusoidal variation, is coming from the core, the unresolved part of the jet. And so we think all that's happening there is that you're getting the fueling is interrupted was interrupted for 20 years. And so that particular part of the jet just didn't radiate for 20 years. And then some more fueling happened, and we started seeing it again. So the prediction is, of course, that as time goes on, we should see that period coming up and up again and again. But that was one of the very interesting things, that A, you would see a sinusoid, and B, it would go away.
Would the gap stay the same or change?
No, I think the gap will be just random because it's just it just depends on when the fuel happens to fall in. But that's one possibility. I mean, that's a possible explanation. I'm sure there are others.
Okay, Tony, the next question is from Kunal, who's working from home and the noisy kids in the background. So I'll read the question. Could the observation simply imply single SMBH precession instead of binary SMBH? Such sinusoids have been seen previously also in Planck data and VLBI data taken by Ken Kellerman.
I think it could be due to, it could be a single black hole due to precession. I think that's a possibility. You can't rule out that possibility.
Okay. Okay, the next question is by Vikram Ravi.
Hi, Tony. Thanks for the amazing talk. And I think it's also really important to recognize the huge effort that you put in during this period you just mentioned at OVRO to keep the observatory going and growing in the way that it is. My question was on the neutrino part of the talk. Maybe can you maybe say a bit about how complete you think the 40-meter sample is relative to the neutrino flux? Is there some guidance from models that?
I wish there were, Vikram. Unfortunately, I don't think we have any good models at all. So what we have done is we've tried to come up with as good a sample of relativistic jets as we can devise, so that we would at least, I mean, I think we're going to be able to do a lot of statistical, checks, basically based on the simulations that we're doing. And so we should at least be able to come up with very good statistics of the likelihood of these of certain types of associations. But at this point, I don't think we have any signatures, although I do think that the possible signature of radio flares coinciding with drops in the gamma ray flux when you get a neutrino is a very interesting one to follow up.
Yeah, for sure. Awesome. Thanks.
Okay, I thought there's another hand. It disappeared. Okay, any other questions? Okay, so Tony, since you explicitly bring out the two retreats we have had, I think I should add a little context here, especially for many colleagues who don't read history and therefore generally tend to remain ignorant for most of their life. I had the pleasure of organizing these retreats, and I was strongly influenced by the ancient Persians, who I believe actually had the most successful empire for the longest time, both in square miles and in duration. And the way they figure out, should we go conquer India or not, is first they have a meeting on one evening and they drink a lot and proposals are made and they arrive at a conclusion. And the next day they recover from the hangover and then drink again. And if the same conclusion is reached, then they're set forth on the third day to the next conquest. And that's a key thing to these retreats, is if you come to the same conclusion after true heavy bouts of drinking, you're on. I know this is perhaps not politically very correct these days. Okay, well, okay.
I don't remember any heavy bouts of drinking at those retreats. Sure.
Oh, well, maybe you are not part of the heavy bouts of drinking. Well, for a guy who keeps betting wine bottles, I think there's some misconnect here that's happening.
Well, maybe I only vaguely remember the.
Yeah, exactly. That's the whole point. Okay. So everyone, let's thank Tony again. Tony would like to meet, once the COVID scare is gone, he'd like to meet especially people who are new at Caltech in his office over the next few months as it gets easier to meet. Okay, so it's time to say bye.
Thank you all very much.
Thank you.